Good evening. I am a educator at Kepler 22B, and today we are going to start our new series, which is known as the POTD series, the Problem of the Day series, in which we shall cover the daily problems that will be provided in lead code and jigs by jigs. We will very soon also start another channel or another series, which goes by the name of contest series, where we will be solving the questions that comes in the context of GFG, lead code and code forces. So today is our first lecture of the POTD series, and today we will cover the POTD of 19th August 2025, that was yesterday, in provided at GFG. The question that was provided in GFG yesterday on 19th August 2025 was farthest smaller right. What is the problem statement? It is saying that you are given an array ARR. For each element at index I, which is a zero-based indexing, find the farthest index j to the right such that ARR of j is less than ARR of I. If no such index exists for a given position, return -1, return the resulting array of answers. Very well. So, the name of the question is farthest smaller right. Very well. It says that we will be provided with an array. Let's say the name of the array is ARR. 2, 5, 1, 3, 2. Now we have to look from the rightmost side, and for each element I we have to find out the rightmost index that is smaller than error of I. The element at rightmost index that is smaller than error of I. For example, for 2, the rightmost element which is smaller than 2 is 1. For 5, the rightmost element is smaller than 5 is 2. For 1, there is no element to the right of 1 that is smaller than 1. So this position will have a -1. For 3, the smaller element to the right is 2. And for 2, there is no further element to the right, so it will be -1. So the resulting array that you will be submitting is, for 2 it is 1 at the index 2. For 5 it is 1. No, so for 5 it is 4 and 2 at the index 4. For 1 there is nothing. For 3 it is at index 4. For 2 it is nothing. So this is the array that you will have to answer to submit. Let us start with the brute force. Before we start with the brute force, this problem will be solved using 3 approaches today. One is the brute force approach, and then there will be 2 optimal solutions. Regards to time complexity, this will have a higher this will have a higher time complexity, this will have a lower time complexity, this will have a no space complexity, this will take space. Very well. So first we will start with a brute force solution. Brute force solution is extremely easy. Okay, so brute force solution is extremely easy. I'm sorry, this got removed for some reason. Yeah. Yes. Very well. So we were provided with an array ARR which has 5, 1, 3, 2. For every element I, you will make a traversal from right to left. Whenever you find the first element which is smaller than this 2, which is let's say here, then you will break the iteration. So let us have the code. So you will first take an answer array. Then you will have a for loop. Sorry. This will be the brute force code. Okay, so this is apparently not needed. I can write it in the lower portion. Sorry. Yeah, I can write in the lower portion as yes. So what will be the time complexity? The time complexity will be O of 1 plus, sorry, O of n minus 1 plus n minus 2 plus dot 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 plus 3 plus 2 plus 1. So it will be effectively O of n square. Yes. So it will effectively be O of n square effectively. So obviously this will provide a time limit exceeded. And yes, what is the space complexity? It is O of 1. Obviously this is a wrong technique. Yes. So now we will start with the first optimal solution. That's optimal one. Many of you might be wondering about whether we can use stack or not. Stack is used in the question next lesser or next greater element. If you have studied these particular algorithms, you will realize that stack is used in these algorithms. But we cannot use stack in this particular question because, see, for 5 here, the next smaller element is 1 and this will be provided by the stack method. However, our answer is the rightmost smaller element and the rightmost smaller element is 2. Now why the stack method is not proper? Let us do the stack method dry run first. So first we will have 2 here, then we will have 3 here. Now whenever you want to bring 1, then what you will have? You will put 3 out, you will put 2 out, sorry, you will put 3 out, then you will put 2 out and then you will insert 1. In this process, you see that 3 and 2, these two values are lost. So effectively, 3 and 2 values are lost and there is no backup stack or backup data structure to store them in order. So the answer that you require, which is 2, is lost. That is why you do not use the stack method. So obviously you will think about how to solve this particular problem using the optimal method 1. Using the optimal method 1, you can solve this problem in a very simple way. And this is the method that is most widely provided in any textbook or any online material that you read, which is the optimal solution 1. Now what is the solution? You have to find out, you're given an array, you're given an array 2, 5, 1, 3, 2. Now for this element 5, let's say, you have to find out the rightmost smaller element. Now, if somehow I can find out all those elements which are smaller than 5 in a sorted order, can I not solve the question? Yes, I can. How? All those elements smaller than 5. One way to is to do this is to store all the elements which are on the right side of 5 to store in a sorted fashion in lieu of the answer. For example, if the answer is 2, then the answer cannot be 3. If 2 is to the right of 3, it is common sense that the answer cannot be 3. So whenever the position of 3 comes, you will not take 3 but you will take 2. When you come to 1 after 3, 1 is less than 2. Since 1 is less than 2, you will take 1 and you will not take 2 because you are taking the numbers or elements that are less, starting from that element to the right. Got it? You are taking, suppose from index I, yes, yes. So from index I to the end of the array, and there are some elements before it. What you are taking nothing but the minimum value that is present from this I to the end. So when you take 3, it is evident that after 3 there is something less than 3. So you are taking the one which is less than 3. But till now 1 is the lowest because after 1, after 1 in this entire sub array, the least element was 2 which was present in the array. But now you are taking 1 which is less than the least element that was present in the array till now. So from 1 to the end of the array, the least element will thus become 1 and not 2 because there is no element less than 1 from 1 to the end of the array. So you're taking the smaller element, the smallest element in this subarray. Now, when you come to 5, it is quite evident that after 5, there must be some element which is less than 5 and that is 1. Why? Because 1 is less than 5. After 5, there is an element 1. Where this element came from, we do not know. But there is an element after 5 which is 1. So we take 1. Now, this is the array that has been created till 5. Now, you have to complete creating the array. So from 2. From 2, you see that on the right of 2, there is some element which is 1, which is less than 2. So there is no point in taking 2 because you will always take 1 instead of 2. If there is something on the left of this array, then from this perspective, you will always take the something which is less than 2, which is 1. Now, you have to check. The answer is you will take 2 and not 1. But here you will write 1. So you have to search in this array from the perspective of this element. You have to search in this array. You have to go through this entire array to find out among the minimum elements, is there existing any element to the right of this particular element, which by default would be in here, which is less than this particular element. So let's say this element is your 9. So here you see 1 is less than 9, and so you write the index as 0. Now you check this one, which is again 1. So the index updates itself to 1 because this is more writer. This one is more writer than this one. Now you come here, you see this is 1, which is also less than 9, but this is more writer. So you will take the answer as 2. 2. Now you come to this, you see 2 is less than 9. and it is more righter, so you will update it to 3. Now you come here and we see the 2. 2 is less than 9, it is more righter, so you will take 4. Yeah, 4. Now let us suppose this number is not 9. Let us suppose this number is 1, yeah, 1.5. So you start from here, 1. 1 is less than 1.5. Let us assume you can mark it up. Like this can be 3 and these can be 2, 2, 2, 4, 4, and supposedly these numbers will be doubled. So for 1.5, we see 1 is less than 1.5, you update it to 0. 1 is less than 1.5, writer 1. 1 is less than 1.5, writer 2. 2 is less greater than 1.5, you will not update. You will not update. And since it is greater, you will immediately break. So 2. Sorry. So 2. For this element, if it is 1.5, answer will be 2. Now you see, we are doing a linear search. Okay, let us write the code of the linear search first. First, obviously, you have to create this supplementary vector. Obviously, you have to create this particular supplementary vector. Let us first create the supplementary vector. Okay, let us first create a supplementary vector. So, vector int. Let us give it a name suffix arr.size. So for int I equals n minus 1, I greater than equals 0, I minus minus. Okay, you have to initialize this suffix vector first. So suffix of n minus 1 equals arr of n minus 1, because if it is the last element, there is nothing smaller than this. So for this particular element, this will be the last element. So it is nothing but suffix of I equal minimum of arr of I and suffix of I plus 1. Sorry, yes. This is created the suffix vector. Now the suffix vector is created. Now see, now you will go through this suffix vector. So let us say you have the vector int answer. Yeah, you will go through the suffix vector. You will start from I plus 1, obviously. You have to go to the suffix vector now. So while going through the suffix vector, you will try to find out the index which is smaller. So it is very simple. If arr of j is if suffix of j, sorry, is smaller than arr of I, then you will immediately put index equals I. Let us say here we write int index equals I plus 1. You initialize it, and okay, this is done, and you will do else break. Now after this step, I am rubbing the above part. After this step, you will do what is that? Sorry. What you are going to do after this is that you will write, since index is given, so yes, answer of I equals index. After that, your iteration is over in this particular array, and you will return answer. This is your algorithm. How much time it is going to take? Of n square space of 1. Obviously, this needs to be optimized. But it is very easy to optimize this. It is very easy to optimize this. How? You see, we are traversing linearly in a sorted array. Why sorted array? Because I told you the supplementary array is sorted. The supplementary array is sorted. One more thing that you have to realize that, which I guess I failed to mention, I forgot to mention beforehand, is that you are doing it 2, 5, 3, sorry, 1, 3, 2. You see, when you are creating the supplementary array, at the positions of minimum, at the positions of minimum, the indexes where the minimums are coming, the indexes where the minimums are coming, this is a minimum, this is a minimum, the indexes where the minimums are coming is exactly the same as the indexes they are present in the original array. Why? Because whenever a minimum is coming at a particular index, at the supplementary index, at the same index, at the supplementary array in the same index, I am providing this number. That is the reason. Now, you have to optimize this particular approach even further. Now, you don't have to optimize this indexing part because it is already like it's a conclusion that I mentioned. The optimization is that you see that this particular supplementary array 2, 2, 2, 1, 1 is sorted. Why it is sorted? Because you're starting with a minimum. If you find something which is less than that minimum, you're taking in that and you're continuing with it. Then you see something which is even lesser, continue with it. Finally, you take the last minimum. So you see, it is an increasing order sorted array. So that is why we can easily apply binary search. Yes. So the code for binary search, I will write it in the editor. As before, we will continue with the creation of these two arrays. Suffix. Now, from here, the binary search will start. I plus 1. Alright. Binary search is very easy. The same binary search. Int value, int index, we will keep the index as like this. Well, let's say it is minus 1. Okay. Let us go to the editor once. You see, the thing is 1, 1, 2, 2, 2. So you're trying to find out, let's say 2. Let's say your mid is here and the number is 9. So what will you do? You will put the index as, since 2 is less than 9, you will put the index as 2. Now you will remove this part and you will focus on this part. So this part gets removed. Why you will focus on this part? Because you have to find a writer smaller. Writer smaller. So you're going to the right side. Go to the right side. So you come to here. Sorry, 0 and 2, 4. So you do the iteration this part. So next one will be 2 plus 4 by 2, 3. Yeah, you will come here. This will be the mid. You will make the index as the mid, and you will come to this part. And finally, when you come to this part, when the binary search ends, the index will be at this 4. Index will be at 4, and then the binary search ends because low becomes greater than high, and then this particular position will get the value as 2. Sorry, 4. So while low is less than equal to high int mid, I'm doing it like low plus high because the constants are low. You try to do it by low plus high minus low by 2. If if suffix of, no, the point is I have to find the minimum one. The minimum one. If suffix of mid is less than equal to, not less than equal to, very sorry, less than, I have to find a minimum, lower one, lesser one, less than error of I, then what will you do? Low equal to mid plus 1, and index equals mid. Else, if it's greater than equal to, then you will have to omit the right part and you have to move into the left part. Why? Because the right part is why right word part is more, and since the sorted array, writer of that right word part, that is from mid to the end, it will increase, but the number is less, so you have to look in the left word part. So high equals mid minus 1. Index is calculated. You will simply do answer of index equals index. No, sorry, by answer of index, answer of I here. And then you will simply return answer. Let us see if this works or not. Might be some syntax issues. Might not be some syntax issues. Yes, it worked perfectly, and we will try and submit it. After that, we will go to the second optimal method. The second optimal method is also quite beautiful. Here, the space complexity of O is O of n. There, the space complexity will be O of maximum of n. Let me analyze the space and time complexities first for you. Let me analyze space and time complexities first for you. Yes. Is the code here? Apparently, it is not. This is a text box. Okay, I'll just copy the code and I will try and paste it, and the pasting has been okay. The pasting is not bad. The pasting is not bad. I really don't know how to make the color white for these, and I won't even try. So who cares? Yes. So I will continue it here. So you see, this part, this for loops takes order of n time, and this for loop also takes order of n times, and this binary search takes order of log n time. Sorry, log n time. So the overall time complexity becomes, sorry, so the overall time complexity becomes O of n plus O of n log n. Now the space complexity becomes O of n for the suffix array plus plus a necessary O of n if required by interviewer. If it could, sometimes interviewers want this thing. This space is nothing but the answer array. Sorry. Here is the second method. Now we will go to the, sorry, this is the first method. Now we will go to the next optimal solution. The next optimal solution is based on the fact that if you encounter a value, let's say 2, you are moving from right to left. If you encounter a value 2, see, this is a very intuitive approach. It doesn't use very high data structures or common well-known algorithms. In fact, this solution cannot be even found in most of the textbook literatures. In fact, I have never found out the solution. I do not even know whether the solution exists or not in any literature or any editorials or whatever, because the solution doesn't exist. Or maybe it exists, but I haven't seen it yet anywhere. Anyway, so hopefully this is a new approach which perhaps I haven't ever heard of. So you have to understand it carefully, very carefully. See, whenever I am at a particular element and it is the last element, or no, sorry, smallest element, if it is the smallest element till now, try and mark from right, obviously from right, from right. Try and mark all elements greater than this element as having rightward index at this element. This definition is good, but it is slightly flawed because you mark it for 2 very well. It is 2 is a small element. You mark anything above it. Let's say it is an index 4. You mark anything above 3. It is marked with index 4. 1 is less, so you do not mark it. 5 is greater, mark it with 4. 2 is not greater, you do not mark it yet. Now you come to 3. You see that for 3, already there exists something which is less than 3 on its right at index 4. See, for 3, for anything above 3, since you're moving leftward, anything above 3 to the left will always have the 2 at index 4 as the answer and not 3 at index 3. So you do not have to count 3. Now come to 1. 1 is the smallest element till now. So anything above 1, you mark it. Let's say 2. You mark it with index 2. Now, will you mark 3? Will you mark 3? No. Because 3 and anything above 3 has already been marked with something lesser, that is 2. Which is still more rightward than 1. Which is still more rightward than 1. So you will not mark it from 3. So if you are at 2, okay. If it is a smaller element, obviously you have to mark them as -1. Smallest element till now. You have to mark them as -1. So you see, if it is a 2, then you will mark anything above 2, that is 3 to 5. 5 is the highest index, as index 4. If it is a 3, you will not mark it. If it is at 1, you will mark 2 to not 5, but 2 as 2. If it is a 5, 5 is already marked. If it is a 2, 2 is already marked. So effectively, you have to mark these. So let us mark these. One, two, three, four. Sorry. These are array indexes 0, 2, 3, 4, 5. This 0 is out of scope, out of bound. You don't have to worry about it. So 3, 4, and 5 are marked with 4. 2 and 2 are marked with, let's say, 2. Yeah, it is 2, marked with 2. Now, you initialize this array as with -1. So 1 is not yet marked because, well, There is no 0. So you will not mark from 1 to 1 perhaps, or 1 to 2 perhaps. Now, this array, we'll just call it a supplementary array. Now, you will, for the final step, you will again traverse in this array. Why? From the right. From the right. If you come at 2, it is a minimum element. See, it is a minimum element. 2 is a minimum element. This is the answer array. Let us say this is the answer array. The minimum element. Minimum element, as I said, always a -1. Now you come to tree. You see the index tree has already been marked with 4. The tree has already been marked with 4. So you will put 4 in here. You come to 1. You come to 1. You come to 1. You see 1 is already having -1. But 1 is the smallest element. After 2, 1 is the smallest element. So you will mark it as -1. Now you come to 5. You see 5 is already marked with 4. Mark it as 4. You come to 2. You see 2 is already marked with 2. You mark it as 2. So this is the answer array that you will return. I hope the intuition is clear. I am going through it once again. Basically, you will, if you find the smallest element till now, you will mark till now from the right, obviously. You will mark all elements greater than this element and smaller, and smaller than previous smallest element. Why? Since they are already marked. They are already marked. And anything greater than the previous smaller element, anything greater than the previous smaller element will always have this particular smaller element, which is at the rightermost than this smallest element, the rightermost as the answer, and not this. So you will mark them as having the rightmost index as this particular element. So this is the intuition. Dry run is also done on this particular array. So let me write a dry code, pseudocode first. Then I will go to the actual code. Yes. Yes. Well, so let me write the optimal code for pseudocode first. Pseudocode seems to be very easy. Pseudocode is actually very easy. First, you will create a supplementary array. How will you create a supplementary array? What is the supplementary array? So first and foremost, you have to find out the maximum, because the supplementary array will be, the size will be one more than the maximum. Why more one more to maximum, one more than the maximum? Because we're starting from 1 and we're counting till the maximum element. So first you will write find the maximum element. Then you will create a supplementary array. Initialize this to -1. Now what will you do? You will fill the supplementary array. If supply of error of I equal to -1, because 3 is already filled by index 4, which have 2, so you do not have to do it for 3. Equals -1. There. If it equals -1, then what will you do? You will start maxi from one more sorry, yeah, from one more to the maximum from that number, let's say from the smaller number, from right you are moving, from right you are moving, from one more than the smaller number, okay, one more than the smaller number, I don't know why this keeps happening, from one more than the smaller number you will mark everything to be the index of the smaller number. What do you mean? I mean that from one more, suppose your smaller number, smallest number till now is 2, from 3 to the maximum, from 3 to the maximum, you see they're all to the left of it, they're all to the left of it, they may not be to the left of it at this moment, at this moment right now, they may not be to the left of it at this moment right now, they may not, because they may be to the right, because you never know whether 4, if you are at a particular index 2 or a particular index 4 which is having a value 2, you never know whether 4 is to the right of 2 in the main array or to the left of 2 in the main array, it might be to the right of 2. So it might happen that in supplementary array you are putting some things, like putting the index of some things, some numbers which are to the right of 2, to the right of 2, but you are putting it, but you do not care, because you are doing what you are supposed to, you are writing the numbers which is supposed to be, which is writing the number which is supposed to have the minimum as this one. But and sorry, and this particular problem, that whether it will be to the left of it, whether it will be to the right of it, that particular problem will be solved in the next iteration when we will be moving from right to left in the original array, and we will keep a track of the minimums. So you see, it might happen that whenever 2, which is the last element 2, you remember when you was making the supplementary array, you put 2, you put something to 2, you put something to 2, I remember, but you put, I think, index 2, yeah, index 2, which was containing 1, so when you are at the last element, when you are the last element, 1 has not yet been visited, so what you are doing, since it is the smallest element, you will putting as a -1, coming to that. But yeah, that problem of whether it will be to the left of it, whether it will be to the right of it, that problem will be mitigated in the next iteration. In this iteration, we are simply doing what we are supposed to do. We are marking everything above that, above this particular number, above, let's say 2, 3 to 5, 3 to maximum, as having the smaller number as 2. Simply that is what we are doing. Coming to that, the other one, yes. So supply of I, sorry, supply of error of I. So supply, I'm very sorry, I just lost track. J is error of I plus 1. So supply of J, yes. So supply of J, supply of tree, what will it be? It will be the index. It will be the index of the current element, which is I. Right, so don't seem to have any more space in here. Okay. I don't think I can increase the space. Okay, I'll keep it here and I will continue writing. Anyway, if supply of error of I is equal to -1, then if only for example, for 3 you will not do this. For only the minimum, only the minimums you will do this. So 3 to 5 marked, then 1 to 2 marked because 3 is already here, and so on. So this creates your supply vector. Yeah, this creates your supply vector. Now the supply vector has been created. Now the main task comes. Till now the supply vector has been created. If any problem, you may see the screen. I will anyway perform it in a code editor very soon. Now the supply vector is created. Now what will you do? You will move from left to right, right to left, sorry. You will move from right to left. Now what will you do? You will see if it is the smallest or not. So for that you have to keep a mini count. And for the sub array, which is containing only one size, The element in the sub array, which is 2, it is the array. This is the thing that we are starting from. The element in is one size sub array is always the minimum element. So this will be nothing but error of n minus 1. So there are two conditions. If it is the minimum, or not. If it is the minimum, you will do what? You will first assign this as error of I, mini, as error of I. First task you will do. And the next task you will do is answer of I equals minus 1. Now, if it is not the minimum element, then it's the index of the original array, which contains the element from the rightest side, which is smaller than this particular element, is stored in the supply array at a corresponding index of that number. So, answer of I will be nothing but supply of your error of I. I believe this ends the algorithm and you will return answer. So let us perform it in a code editor. There is one important thing that we missed in our code. One very important thing that we missed in our code. When we are writing this particular line, this line, sorry, then you are in a for loop to maxi. You're updating this range with I. You're mistakenly forgetting one more thing. So if you're at 2, then you are already done with 3 to 5, and 3 to 5 will always have this thing as 2. So when you're coming to 1, you will not need to do 2 to 5 because 3 to 5 this segment is already present. So you will do 1 to 2 in the next term. So you have to update the maxi to be error of I. Sorry. Okay. You have to keep a track of the minimum as mentioned in the algorithm. If error of I is less than min, there will come a first case and then there will come a second case. In the first case, what will happen? You will update it first. And if it is the minimum value, To the right of the minimum value, there can be nothing less than this. So answer of I will be given as -1. And here the answer of I is already ready in the supply array. And you will at last return the answer. There seems to be some kind of a problem. 2 is supposedly okay. It is a very important, is a very big thing that I actually overlooked. Is because I need to look for lesser element, not less than equal to element. Lesser element I am supposed to find out, not less than equal to. It's done perfectly, and let us see whether it is getting properly submitted or not. Apparently it is getting properly submitted, and now I will discuss the time and space complexity. I'll make a try once again to see if it does work or not. I think it won't work, so it's worth a try. It, let's see if I can make the font color as white. Okay. It didn't work, unfortunately. Alright, it is perhaps not working for some reason. I'll do it like this. Let's see if I can. Not working, unfortunately. White, and if I increase the opacity, I don't know what is going to happen. Let's see the text color, if it can be increased or not. Yes, it has. Fine, we don't need it anymore. Alright. Yes. So you see, at this part, maxi calculation, it is often supply calculation. It is very important. Now you see, this part is also very understandable. This part is if else statement, only an if else statement. It is the if, it is the else, and it is the for loop. And if else, so it is if else statement. Now this part is important. See, you are effectively traversing from right to left. That is taking off n. Now that is taking off. Obviously, it is taking off. Now, when you are at an index I, you do not move. Let us say the value is 3. You do not move from 4 to 5. Only when you encounter a minimum element, then you move from mini plus 1 to maxi. And you do not always move to maxi. Once you are done, you make this maxi is equal to mini. So effectively you are moving from here to here first, then here to here, then here to here, then here to here. So effectively you are moving all the way to maxi. Let us consider a maxi to be n, because in our editor it is given as both are given as 10 to the power 6 equal range. So let us consider it as n. So effectively it is n plus n. This is the first n, and the entire movement takes n of n. because entire movement takes an of n. So this is taking O of 2n. So this is O of 2n, this is O of n, this is O of n. So entire algorithm becomes, time complexity becomes O of 4n, and space complexity becomes O of n. This is the final answer. Very well. So this concludes the POTT of 19th August 2025. If there is any further improvements or any further notifications that comes regarding this POTT, it will be explained in later videos. For now, we will meet in the next video with a new POTT problem of, let's say, today or tomorrow or yesterday's lead code. We will see in the next one. So till now, take care and goodbye.